The presence of a solute will affect the properties of a pure solvent, and a number of those properties are what we call colligative properties. So a colligative property is special because a colligative property is one that is changed by the number of solute particles, but not really their identity. So it only matters how many solute particles there are. It doesn't matter what those solute particles are. So we can look at a number of different properties, and I think colligative properties will make a little bit more sense as we look at some of those properties. So let's jump right in. The first one that we're going to look at is something called vapor pressure. So if I have a liquid and I put it in a sealed container, it'll develop some vapor pressure up above the container. So here's my liquid in a sealed container. Some of those liquid particles will evaporate, will go into the vapor phase. And if this is a sealed container, eventually it'll get to a point where the rate that solvent particles are escaping from the liquid to the gas phase is equal to the rate that they're condensing back from the gas phase into the liquid phase. So we'll end up with a consistent number of particles up here and a consistent pressure. So that's what we call the vapor pressure of a liquid. If you think about, a sealed container of water versus a sealed container of something like gasoline, right? If you seal those containers, water doesn't really develop a whole lot of vapor pressure, at least not obvious vapor pressure when you open the container. But if you have like a gas can for your lawnmower, if it's sealed for a while and you take the top off, you hear some gas escape because it has developed vapor pressure. When we add a solute to that solvent gets in the way and prevents some of those solvent molecules from escaping into the gas phase. And because of that, there are fewer gas particles in the gas phase, and the vapor pressure of the liquid that we're looking at is depressed compared to the pure solvent. So when we add a solute, vapor pressure goes down. So vapor pressure depression is a colligative property. Because notice I didn't say anything about what these particles were. I just said that they're solute. And they could be all the same solute. They could be a mixture of solutes. It just depends on the number of them that are present. So there we go, vapor pressure depression, colligative property. Another colligative property that's related to this that you may have some firsthand experience with has to do with boiling point. So what does it mean for something to boil? Well, vapor pressure, you can imagine on that last slide, if you change the temperature, you change the vapor pressure. Increase the temperature, and it's easier for those liquid particles to escape into the gas phase. When we increase the temperature enough so that the vapor pressure is equal to the atmospheric pressure, that's what we call boiling. So if vapor pressure is depressed by adding a solute, well, boiling point must be impacted as well. So if I'm depressing the vapor pressure by adding a solute, then I must have to heat that liquid, that solution, more to get it to its boiling point, to get it to the place where the vapor pressure is equal to the atmospheric pressure. So when a solute is added, the boiling point is elevated. So boiling point elevation. And you may have used this, you may have practiced this in the kitchen. If you're, especially if you're making like candy, like hard candy or caramel, when you add a bunch of sugar, when you add a bunch of sucrose to water, the boiling point goes up and up and up as you add more solute, more sugar to the mixture. So when we're looking at boiling point in aqueous solutions, every time you add a mole of solute particles, you increase the boiling point by about 0.5 degrees Celsius. So that's how much boiling point is elevated in water. The boiling point elevation constant is different for every liquid. But this is the one that's, this is the constant for water. It's a handy one to think about. The other thing to remember here, we're talking about colligative properties that depend only on the only on the amount of solute particles, not on their identity. So if I go from something like glucose to something like chromium nitrate, right? Now I've got an ionic, so every mole of chromium nitrate that I dissolve in water gives me a mole of chromium ions and 3 moles of nitrate ions. So it gives me 4 moles of solute particles. So dissolving 1 mole of chromium nitrate in a liter of water will increase the boiling point by 0.5 for each of those 4 particles. So that would increase it by about 2 degrees Celsius. Well, if boiling point is affected, you expect freezing point is going to be affected as well. So what happens when things freeze? When a solvent freezes, we drop the kinetic energy of the particle enough so that they slow down, and suddenly intermolecular forces can get them to stick together, can get the particles to stick together. Oftentimes this happens in a crystalline solid, so things have to be very organized. If I add a solute, I've disrupted that organization. So I need to slow things down even more in order to get those solvent particles to freeze. This is freezing point depression. When I add a solute to a pure solvent, the freezing point is depressed. It goes down. And again, if we're thinking specifically about water, the freezing point decreases by about 1.9 degrees Celsius for every mole of particles, or of solute particles that we add to the solution. So freezing point is affected more than boiling point is. And again, if we're talking about anything other than water, this number is different. But for water, it's about 1.9 degrees C. So when we're using ionic compounds, if we use something like nickel chloride, we'll get 1 nickel ion and 2 chloride ions, so a total of 3 moles of solute particles when it dissolves. We see this every year, and it's coming up quick. How do you melt the ice on your sidewalk? You throw salt on it. Well, that works because of freezing point depression, and the reason we use salt instead of sugar is because we just get more moles of solute particles from the salt than we do from the non-ionic solutes. The last colligative property that we're going to look at is a very, very important one biologically speaking, and that is osmotic pressure. So osmosis is the process by which solvent particles can pass through a membrane, but solute particles cannot. So I've got that membrane, and I can pass solvent back and forth across that membrane, but I can't pass solute across that membrane. Solvent particles go from the more dilute side to the more concentrated side until they're stopped by osmotic pressure, or until the two sides have an equal concentration, right? So that's ultimately what is trying to happen in osmosis. It's trying to equalize the concentration across a membrane, but sometimes we can stop before the concentration is equal because of osmotic pressure. Osmosis and osmotic pressure often use a concentration unit called osmolarity, which should look kind of familiar because osmolarity is just molarity times the number of particles per formula unit, right? So every time we've been looking at ionic solutes, we've kind of been using osmolarity. We've been multiplying by the number of solute particles per mole of solute to get our concentration. Well, really, we were looking at osmolarity there. So works the same way. It's just a matter of increasing concentration and decreasing concentration based on the number of particles per mole of solute. And like I said, osmosis and osmotic pressure are incredibly important. They are, as I say here, sort of the pumps of biology, right? They drive many, many, many biological processes, because things like cell walls and cell membranes are really semi-permeable membranes that osmosis can happen across, or in some cases can't happen across by their nature. So osmosis and osmotic pressure is a very important concept to have an idea of. But really it's just those two different concentrations that are trying to get to an equal concentration. We use colligative properties every day in various ways, and we'll continue to look at some of these properties and how we can influence them by setting up our experiments. So practice these, and I will see you next time.